Hi everyone, in this video I'm gonna show how to solve this problem. Suppose we have a measure space and the measure of whole space is finite and we have a sequence of measurable bounded functions uniformly converges the sum function f. Then we're gonna show that the integral of the sequence of the functions would also uniformly converges the integral of f. So we can always use dominated convergence theorem to solve those kind of convergence problems. But in my video, I'm gonna use another way to show that we can also at least solve this kind of problems without using the DCT. So first, let's recall the definition of uniformly convergence. So if a fj of x converges to fx uniformly, then for given epsilon greater than 0, we can find some j or we can find some n such that when j is greater than or equal to n, the absolute value of or the distance of fj and fx would be smaller than epsilon. So also notice that we have the boundedness assumption in this problem. So the thing is we can find some upper bound for such value. So essentially we're gonna show that if this integral converges to this one, we're gonna have fj d mu minus, so the distance between those two integrals would be smaller than epsilon, or it goes to 0, let's say. So we're gonna find some bound for this function. So first notice as the integrals are linear, so we can write this into fj minus f d mu. Then we know it's has to be smaller than the integral of fj minus f, the absolute value of fj minus f d mu. And so as we know that for large enough n or large enough j, the distance or this thing would be super small. So we could just take the supremum of fj minus f and we take limit, or we let j goes to infinity. This one would definitely goes to 0. And then we also have another assumption in the problem, which is the measure of the whole space is finite. So then we can bound this integral to be by using the supremum of fj minus f times the measure of the whole space. So as this is finite, we can say it's like c or some k, some constant. and this one which goes to 0, which means the whole thing which goes to 0. So that's the proof of the problem.